So this is for estimating the torsional stiffness of a member to, let's say, if I want to quickly calculate how much torsion that I can transfer to the primary girder. So that is function of your torsion stiffness. Okay, that's what we said. When we have a primary girder and secondary beam, primary girder, when it is undergoing rotation, the primary girder torsion stiffness it will contribute, and the secondary beam will contribute in flexion. So at the joint, when you are calculating relative stiffnesses, you have to include torsion stiffness of the primary girder and the flexural stiffness of the secondary beam. So accordingly, you can see how much moment you can transfer to the primary girder. Now let's see how to calculate torsion stresses. First, let's focus on plane contact. Okay, so there are different theories that have been proposed in the past. One theory is called soap film analogy. So depending upon the cross section, what we are saying is, let's say you have a square cross section or a rectangular cross section or a circular cross section. If a soap film bubble is forming on the surface of this cross section, depending upon the slope of this film, it gives an idea what kind of shear stresses you are going to have. So that is the soap film analysis. So for example, if I take a circular section. So let's say I want to visualize how the shear stresses are going to be on a circular section. So what we can do is, let's say you take a plate and then cut a small circular cross section where you want to visualize. Okay, in that circular plate, if let's say a soap film, or let's say I put a small membrane, or a, let's say small like a rubber which is very flexible, and then if I start inflating, then when I start inflating, what will happen? You're going to get this kind of a surface. Okay, so which is also called a soap film, or sometimes people also call it as a membrane analogy. Okay, so membrane is just like when you say that I have a, let's say circular opening over which I apply a rubber membrane, and then I start pushing air through it, so that the membrane will inflate and it will take this form. So, or in other words, this shape is what it is going to take. Let's say for a circular section, this is what it is going to take. What this theory says is if I take the slope of this soap film or a membrane, if the slope is 0, it is going to tell you that there I am going to get 0 shear stress. If the slope is maximum, that is where I am going to get maximum shear stress. So the shear stress is proportional to the slope of this surface that I am going to form. Either you can assume that like a soap film is forming, a bubble is forming on the surface of the cross section where you're visualizing, or you put some rubber membrane, and if you start inflating it, what kind of shape it will take, then you start measuring the slope. So shear stress is proportional to the slope of that surface. So the distribution of shearing stresses on cross section can be visualized using the soap film analogy that I talked about, or this is also called as membrane analogy. Okay, so the equations for the slope of the soap film or an inflated membrane on the cross section are actually analogous to the equations for shearing stress. Okay, this is actually Prandtl's theory and membrane theory. So he found that this kind of slope is actually giving an idea of shear stress, which is what was derived theoretically by Saint Bernard. So the distribution of shear stresses can be visualized by cutting an opening in a plate that is proportional to the shape of the cross section that is loaded in torsion. Okay, so you take a plate and you cut an opening. If you are taking a circular section you want to do, you cut a circular hole, or if you are doing a square, you cut a square hole, and then you visualize if a soap film is forming on that, or you attach a membrane and then inflate it, whatever the surface that it is going to form. The slope of that surface that is going to give you an idea how much the shear stress is going to be existing at that point, right? So the slope at each point in the membrane is proportional to the shearing stress at that particular point. Okay, so you can see that at this point the slope is 0. Okay, so that is what we saw. And this point, if you see, the slope is maximum. Okay, so that is why you have maximum shear stress. Shear stress is 0, and you have tau max. You know. So a circular section, you'll have maximum shear stress at the periphery and 0 shear stress at the center. So that is exactly what it is being reflected here. Now let us see again circular section. This is what we said, and that is how we get maximum shear stress here, right? And then zero shear stress here. Okay, so circular hole in a plate, or you put a soap film. How the shape of the film will determine how the shear stress distribution is going to be, right? And we can calculate again. Tau max is basically torque multiplied by radius divided by polar moment of inertia. Now let's see for rectangular sections how this behavior is going. And you can see that for a rectangular section, again, if I in a plate I cut a, let's say, rectangular opening, and then I put this light membrane or a rubber sheet, very thin rubber, and then if I start inflating it, this is the rubber is going to inflate in this form. Okay, so you're going to have very small like this, and you're going to have like this and like this. Okay, so from the surface you will find that this slope is again 0. Okay, similarly this location also slope is 0, and at this location again at the top you will find that slope is 0. Okay, but however if I look at this location, slope is maximum. Okay, so that is exactly what it is giving. If I look at the corner, I'm going to get 0 shear stress here, and then maximum will be somewhere in between. Again, it will become 0. If I'm looking at the mid location of a cross section, or one side of the cross section, again you'll find the slope is maximum here, so shear stress is also maximum. If I come to the center again, the slope becomes 0 and shear stress becomes 0. Right? So this is the shear stress distribution that you're getting in a rectangular section. So that's what we saw. Right? So this is one quick way of visualizing what kind of shear stress distribution that you will have in the cross section. Okay, so the tau max again is given by applied torque for a particular cross section divided by alpha into x square y, and where x and y are basically short and longer dimensions of your cross section, and alpha is again a sectional parameter that is given by 1 by 3 plus 1.8x by y. So these are all coefficients or constants that are given by Saint Venant based on his experiments and his semi-inverse approach theory. Now shear stress, maximum shear stress, let's say you have a flanged section, then how do you calculate your flanged section? So again, shear stress is given by the particular applied torque in a cross section divided by summation of x square y by 3. Now, why is the summation coming? Let's say if I have a flanged section like this. So then what I have to do is I have to divide these things into, let's say, two elements. Okay, so this is element number 1, this is element number 2, and then for each element, you find now x is this shorter dimension, y is this longer dimension. For this dimension, then it is going to be x, and this is going to be y. So you discretize these in such a way that you get the maximum value for this sigma x square by y, x square y by 3. And then you find your maximum shear stress. Okay. So for a flanged section, you discretize the section into several rectangles, and then you sum all these values of x square y by 3 so that it gives a maximum value, and then use them to calculate your maximum shear stress. Now let's take another thing. So now we are talking about how the shear stresses are going to evolve, and this will become the basis for further equations that we're going to use it in our design. There is one more theory that was proposed, is basically a thin wall tube theory, okay, which is a very elegant way of representing the torsional behavior. Let's say I have this kind of thin wall tube that is subjected to a twisting moment like this. So it's a continuous thin wall tube where the torsion is applied along the longitudinal axis. If I take the small element A, B, C, D, and then look at what kind of forces that are going to develop, and we have seen that this is a free surface. You will not have any shear stresses. So the shear stresses are going to develop only like this, right? Right? So now this tube need not be a constant thickness. At one location you can have T1 like this, and another locations you can have T2 like this. So the thickness need not be constant. Okay. So, but however, you will find that. So let's look at now what is the shear stress. So for example, in this thing, now depending upon the shear that is acting, the shear stress can be calculated from VAB divided by the area of that particular section. Okay. For example, this AB will have thickness of T1 and then some width that you can calculate T1. Similarly, you can also calculate your tau 3, okay, which is acting like this. Okay. So similarly for tau 4 and tau 2, on all the four faces, you can calculate what are the shear stress that are acting. Now, let's say if I invoke let's say this is my horizontal direction x. If I take the sigma fx is equal to 0, then you'll find that VAB should be equal to VCD. So I can write like this, and then that indicates that tau 1 that is acting, okay, which is VAB multiplied by D1 and dx. Okay, this is a small element that we are taking, which is your dx, length is dx. Okay, so T1 and dx is nothing but the area of that particular plane on which these forces are acting. So here you can see that VAB means T1. So this location is T1, tau 1 is acting. Tau 1 multiplied by T1 times dx is nothing but your shear VAB. Similarly, tau 2 multiplied by T2 into dx is going to be your VCD. So they have to be equal. Now dx is same, so they will get cancelled. So what we can find is tau 1 T1 is equal to tau 2 T2. Or in other words, we can say that the product of shear and the thickness, shear stress and thickness should be same across different phases. Okay, so this is what we call this tau into T, which is what we call that as a shear flow, which is actually denoted as Q. So tau into T in any of these planes has to be constant. Or in other words, the shear flow has to be constant. This is similar to when a water is flowing through a, let's say, a pipe. Always the flow of the water is going to be constant. Maybe the diameter of the pipe can change. Even though the diameter of the pipe is changing, the flow will always remain constant. The same way, shear flow is always going to be remaining constant, irrespective of the thickness of the element at which you are calculating the shear stress. Now, why we are going to use this is we are going to find out an expression for shear stress in terms of a thin tube theory, because we have find that the shear stresses are maximum around the periphery of the cross section. So, so there's a theory says that okay, even for a solid section, I can assume this to be a thin tube, and in a simplified way, I can calculate the resistances or the shear stresses. So that is the idea. Now let's say I am taking this kind of a thin wall tube, and let's say this is your shear flow, and the total force that is acting is going to be q into ds if I take a small element ds, and this element, let's say this phase is at a distance of r from this axis of this tube, which is r. Okay, so now we can find that for an applied torque, let's say like this is your applied torque T, how do we get my resistance? That is going to be q into ds, which is the force multiplied by the lever arm r, is going to be basically q into ds is your force and r is the distance. So force times distance is basically the twisting resistance that I am getting for this applied torque. But this I have to integrate over the entire perimeter of this tube. Okay. So when I do this perimeter of the tube, we know that the shear flow is constant. Irrespective of whether the thickness of the tube is changing, shear flow is constant. So it will become R into ds. So when I integrate this R into ds, and then when I multiply by the shear flow, I will get the torque. So this is basically externally applied torque, and this is your internal resistance. Okay, these are internal resistance, right? So you will find that from geometry, this R into ds, if you look at it, this is your ds and this is your R into ds. So when you do R into ds, actually what you are getting is this, the area of your rectangle. So from geometry, we can say that for each small element that I'm taking, when I do it for the entire perimeter, this will work out to be 2 times your area that is embedded by the center line of this tube. Okay, or in other words, so if I draw a center line like this, right? So whatever that is the area that is embedded within that is basically nothing but your A naught. Okay, this is your A naught. Okay, so when you do this integration, this RDS over the perimeter will work out to be 2 times A naught. So the torque, the externally applied torque should be equal to 2 times the shear flow multiplied by the area with this within that center line of the tube. Okay, so and we know that. So now how do we establish now? Now we can write Q as T divided by 2 times A naught. And now what is Q? Q is nothing but tau into T. So shear stress can be written as T divided by 2A naught divided by thickness of the tube. Okay, so depending upon where you are calculating, of course the thickness is going to change, right? So in this way we can relate shear stress to the applied torque. Now let us look at how the principal stresses are going to be. For us, as we have seen it in shear, for me, if I am able to convert the complex stress state into an equivalent principal compression and tension, then I can compare with my actual material properties to see whether that element is cracked or element is going to crush. Okay, that is the whole idea. So Mohr circle is one very elegant way of converting the in stresses in 2D into uniaxial stresses. Similarly, Mohr circle can be expressed in the form of 3D also. It will become a sphere. So anyway, in this case, let's look at what happens in shear stress due to torsion. Okay. So different elements, when I look at it, you're going to develop these kind of stress states. For example, you have a square beam that is subjected to torque like this. Okay. It will go like this. So then if I convert them into an equivalent principal stress, okay, we know that you know the stress state, pure shear, and for pure shear, you know that how the Mohr circle is going to be looking like. Let's say tau 1 sigma. You have no normal stresses, so the circle is going to be right at the center, and you will have equal principal compression and tension. So you know that from the strength of material, so sigma 1, let's say sigma 2, they will be equal, right? So for each element that is torsion is going to create pure shear stress, no normal stress. So at each element I can calculate what are the principal stresses, and you'll find that the cracking is going to go in the spiral form, because it's going to, because again at the corner you know that it is going to have a zero shear stress. Okay, that is why the element angle will keep changing, and you will have these kind of cracking pattern which is going to spiral along the length of the member. So that's why you get the spiraling crack due to torsion because of the applied torque. Now let us see what happens to the same principal stresses when you have both torsion as well as shear. Okay, and you will find that here you will find that the direction, if I took it, let's say this is your front face and this is your back face. Okay, you'll find that the shear stress directions are going to change depending upon what plane that you're looking at the element. Okay, but in shear, if you look at it, this is the shear force that is acting. So the shear stress here and here, they are in the same directions, right? So when I keep adding them, then what will happen? So if I look at this front face, this is the direction of your shear, and this is the direction of shear stress due to applied shear. So you see here, this and this will add up. Okay, but if you look at in this back phase, my shear stress is going to be going up, but due to shear it is going coming down. So this and this will subtract each other. So in front phase, the shear stress due to torsion and shear is going to add up. At the back phase, it is going to subtract each other because they are in different directions. So because of that, what will happen is whenever you have an element that is subjected to combined shear and torsion, your crack angle is going to keep changing. So for example, initially when you are adding up, of course it is going to go like this and spiral, but in the on the other side, the shear stresses are getting nullified. The both the shear stress from torsion and shear are negated by each other. So here mostly the cracking will be governed by bending because torsion and shear are counteracting each other. So you will have these kind of a more or less a vertical crack because you'll have very low shear and the behavior on that phase will be governed by the normal stresses that are acting due to bending. Because here we are talking about bending moment also because bending moment is creating normal stresses. So that's why we are not including here. We are looking at only the shear stress. So what I'm trying to tell here is in a cross section, you will have torsion that is going to create shear stress, shear that is going to create shear stress, bending moment that is going to create normal stress. So depending upon the element, whether you're looking at the front face or the back face or top face or bottom face, the stress directions also will play a role. And one side you will add up the shear stress and other side the shear stress will get start negating each other. So because of that, we need to be careful. So as we said, shear stress subtract on this face due to shear and torsion. Predominantly the cracking will be governed by bending. That's why you have more or less a vertical crack. Now let us see what happens to plain concrete and reinforced concrete. And we have seen this direction of the cracking is going to change and you'll get this kind of 45-degree crack and it is going to go like this and go like this, blah, blah. Right? So when this beam is subjected and we also know that the shear stresses are going to be maximum in the outer periphery. However, here it is going to be 0. Okay, we know that here it is going to be 0 and then I'm going to get 0 and then I'm going to get like this. Okay, so that is understood, right? So you will find that this is the torsional stress distribution and and reinforced concrete we put a lot of steel and concrete in general it's actually as a material if you look at it whether you test in compression or tension up to a certain point it is actually elastic and then it becomes nonlinear and it becomes inelastic. Okay, so you can the shear stress distribution either you can model this as a elastic stress distribution or because we are putting a lot of reinforcement, we recognize that that material is actually not elastic, it is inelastic. You can model the shear stress distribution as inelastic also. Okay, or sometimes to simplify what people do is okay, anyway, we are putting a lot of reinforcement, and after cracking, the material becomes inelastic. So I can simplify them as a plastic behavior, assuming that everywhere I'm going to have a same shear stress. So you can model it anyway. So people have come up with different theories, either assuming elastic behavior or inelastic behavior or plastic behavior. Okay, so for these kind of elements, when I'm subjecting them to torque, and if I start measuring the twist of this member, and if I plot this torque versus twist, you will find that for a plain concrete with no reinforcement, soon after this reaches principal tensile stress, okay, when F1, then it is going to crack, and then after cracking, nothing is there to arrest this cracking, so it is going to reach failure. So for a plain concrete, the applied torque when it becomes TCR, which is a cracking torsion moment, then it is going to have failure. The same element when I'm putting some minimum amount of steel, that is basically for torsion, you need both longitudinal steel as well as stirrup. Okay, so because when you're twisting an element, you'll find that the spiral crack is going to form and it is going to elongate the member. So when the member is elongating, you'll find that I need to put additional longitudinal rebar, right? Because the member is elongated. So to when it is member is elongated, the entire length of the member or along the cross section, you are having tension, longitudinal tension also that is developed. So let's say for that member, if I'm putting light reinforcement, you'll find that the ultimate strength is not going to be very different to that of your cracking torsion moment. Same beam. Now, if I put, let's say, 2% of steel, both for longitudinal as well as for stirrup, as a volumetric ratio, then you will find that again you will have some ductility. However, again the ultimate strength or ultimate torque is not really significantly different to that of your cracking torsion moment. Now, if you put lot of steel, again you will get some marginal improvement in your ultimate strength compared to that of a cracking torsion moment. However, that increases again, it's not going to be very significant. So you will find that putting a lot of steel is not really going to help in improving your torsional strength significantly. Unlike in flexure, you would have seen that. Again, in shear also, you would have seen that by putting a lot of steel, we can augment your capacity. Right? In flexure, you will find that the cracking would be in the order of 15 to 20% of your ultimate strength. Right? Similarly, in shear, if your shear demand is high, more than your cracking capacity, sorry, concrete capacity in shear, then you can put so much amount of stirrup to augment the capacity. But again, there is a limit for your VS. Again, why we should not have principal compression failure also. So that we have talked about it in the previous module. Anyway, so in torsion, putting lot of steel will help in restraining the crack and reducing the twist at our service loads. However, the strength increase is not going to be very significant. Right. So now I need expressions for calculating the cracking torsional moment capacity, and that can help me in idea how much amount of steel that I need to put. Let's see how to calculate this cracking torque. So we're going to use this plasticity theory. So as we have seen, concrete is neither elastic or inelastic, and we are putting a lot of steel also. So we can assume the shear stress distribution to be plastic. Or in other words, the entire area is going to reach the same level of shear stress. So let's say I take this typical rectangular section with B and D, and let's say this entire section is getting plastified with maximum shear stress tau max. Okay, so if I divide this sections into triangle and these kind of trapeziums, okay, so what you find here is I can calculate tau max. So I can calculate the values for your VH and VV. So how do we do that? So if you find that is basically nothing but the area of this triangle, which is basically, if you see, this is b by 2 and this b, so the area is going to be 1 by 2 multiplied by b into b by 2, which is basically b square by 4. So, and the entire section is now plasticized, and it is having a maximum shear stress. The tau t max, what the concrete can take, that is, I can always express that in function of a square root of your FCK. Usually tensile strength or shear strength is expressed as a function of your square root of your compressive strength. So I can fix a value for this tau t max. Okay, that's based on experiments or based on some experience. We can come up with a value for this tau t max. So like this, we can calculate your shear resistance. Like this, VH will be tau T max multiplied by B square by 4. Similarly, VV is this is your area, trapezium. Then I know the geometry, which is going to be basically D minus B is your this shorter width, and the longer dimension is your D. So if I do that, then VV is going to be tau T max multiplied by BD by 2 minus B square by simple geometry. So basically, I'm calculating this area. Okay. So the area is basically this area multiplied by the shear stress will give me force. So now for the applied torque, I am calculating what is the torsional cracking moment. So all these things is going to act like a couple. So basically VH multiplied by, let's say, this multiplied by Z1, which is this, is going to give me one torsional resistance. Similarly, VV multiplied by Z2 will give me one torsional resistance. When I add them up, that is the total torsional resistance at cracking. So if you substitute again from geometry, we can calculate where this centroid is going to be of these areas. That is nothing but D minus B by 3, and Z2 is going to be this. The pure simple geometry calculations, right? So when I plug in this Z1 and Z2, and anyway we have calculated VH and VV. So when you substitute that, you will find that the torsional cracking moment can be expressed in terms of tau T max and some geometry like this. So when you simplify all these things, you will find that TCR is nothing but tau T max times B square by 2 times D minus B by 3. So this is the expression that is given in your code as well. So again, we made a very simplified assumption that the entire section is going to resist the maximum shear stress of tau T max. Again, I go back. So why is this thing coming? So this is coming from this red color curve, that what we have assumed the entire section is going to have same stress. Okay, so this is an assumption that I've made to simplify in a simplified way to calculate uh, torsional cracking moment.